Okay. So, hi everyone. Welcome to the verification seminar series, and we are happy to welcome Jan Křetínský as a speaker today. And Jan is a professor for formal methods for software reliability at TUM in Germany, and of course, he's done a lot of very interesting work in verification synthesis, verifying and explaining AI, probabilistic model checking, automata theory, temporal logics, and various other things. And today he'll be telling us about learning winning policies in LTL synthesis. Okay, so over to you, yeah.
Thank you very much. Thank you for the kind introduction, and thanks for inviting me. So it's perfectly correct what you have said about Technical University of Munich. At the same time, I'm also a professor at the Maastricht University of Brno, actually my hometown, where I'm gradually kind of coming back to. This is a long process that will take a number of years, but my group is now distributed over the two cities, Munich in Germany and Brno in Czech Republic. And I'm mostly in Brno. If you want to visit me, I'll be very happy to discuss. Many of my people are still in Munich, so whenever you turn up in Munich, also be very welcome and come and visit us. This is a work with a wonderful bunch of students of mine, some of whom meanwhile graduated, went through their postdoc and got their professor positions at various places. And I'm happy to tell you about how I see the development of the area of LTL synthesis, quite dynamic area, although very old one at the same time. And I'm going to first have a kind of look into the past, survey various approaches that there have been, identify what were the shortcomings, and then see what we can do about it using learning. And for all that, I will be more than happy if you interrupt me at any point of time asking questions. I'll be very happy to keep this interactive. We don't really have to cover everything. It's up to you. So feel free to interrupt anytime. All right. So let me start with saying that synthesis problem is actually one of the old and central topics in computer science, dating at least as long as 1957 in Church's paper, where he maybe I can afford to read this archaically sounding statement or definition of the problem. Given a requirement which a circuit is to satisfy, so I mean thinking in terms of hardware circuits back then, we may suppose the requirement expressed in some suitable logistic system, which is an extension of restricted recursive arithmetic. So he is having some logic in mind. In particular, it would be some logic talking about what happens after what, and so it hints at temporal logic already back then. And he says that the synthesis problem is then to find recursion equivalences representing a circuit that satisfies the given requirement, or alternatively to determine that there is no such circuit. So back then he states in this archaic terminology that we essentially want to find a finite state machine doing the following job. We can play a sort of a game where you are in the role of the input player and you are giving me inputs. So you start with one, and then you go on with the bits one by one. And my task is to reply one bit at a time to your bit, so that the combined words are then satisfying the desired relationship. So this is, of course, a bit informal. Let me be a bit more precise at this point. I will try to be informal in the rest of the talk, but let me be at least quite precise with the definition of the problem. So the idea here is we want to synthesize this black box, this function f, that is doing the job of creating outputs for the inputs so that the given specification is satisfied. And now, to be more precise, we need to say that there are input and output signals. You can see them as input and output atomic propositions if your specification is in a logical form. And to be more precise, I state here the input stream is a sequence of valuations over the input alphabet. So you can see this as a set of atomic propositions that are valid at that time point, and it's chosen from the part that belongs to the input player. And the output player is supposed to respond with outputs that are valuations over the output atomic propositions in such a way that it always only sees what has happened so far. So it doesn't really see the future. It only sees the current prefix of what the environment has been doing. And this way we are generating the output stream. And now the requirement is that if we now merge these two streams in a pointwise way, we do a union. So we put the input and outputs together. This generates a valuation over the combined alphabet, over the combined input and output signals. Then such a word then satisfies the given requirement. The requirement, you can think of it in this talk specifically as being an LTL formula, but in principle, nothing prevents you from thinking about your favorite temporal logic, be it one on continuous signal, so it can be STL, be it one that is more time-oriented, like MTL, MITL, or whatever fits your needs. The work that we have done is mostly on LTL because of its simplicity, but nothing prevents you from thinking onward. To give you an example of this, let me first consider a very, very simple safety requirement, which says that at all times, so this is the LTL globally operator, saying that at all times, A, X, or B should hold. So A is here an input variable under your command. B is something that I can emit, so I can either say empty set or I can say B, saying that B is valid at that time point. And I want to achieve that no matter what you say, at every time point, the combined valuation is satisfying A, X, or B. So of course, when you say A, I then say empty set. If you say empty set, I say B. So you see that for that, you don't really even need any memory. You can directly answer with actually like that. I mean, you have just this mapping, and that's it. Now, considering a slightly more involved example, here we have the simple requirement that at all times, whenever there is a request, which is again under your command, I am supposed to, at some point in the future, emit a grant. And here, one way of proceeding is that maybe you only, or you can emit a request whenever you want, and I'm going to emit grants in, say, every even step. So then, of course, I can satisfy this requirement because in every second step, I will just emit a grant, which is then making the whole requirement satisfied. For that, I don't need much memory. I mean, I could have said I emit grant at every step. Maybe something else prohibits me doing that. I could have another, and that would be a typical practical case, another requirement that infinitely often I am not emitting grants. So it's not like I always emit a grant. And then maybe you need a memory. You need to count until 2, in my case, in this simple strategy where you emit in every other step, you emit the grant, or you remember that there was a request and only then you emit grant. So you need a bit of memory, which leads, of course, to automata theoretic solutions, as we shall see in a minute. Let me mention that this framework of synthesis, as we have seen it here, has been independently reinvented in several communities, starting with the theoreticians, going over supervisory control and in control area, to the modern people in verification. And I think this also it shows the usability and usefulness of this concept. And I'm going to now argue that this is not only a conceptually useful concept or framework, but also a practically useful one, although it doesn't look like that, or didn't look like that for decades, actually.
So Jan, I had a question, Madhukar here.
Yes, please.
Yeah. So in the last example, when you had output the grant in the second time, you had output a grant by seeing requests twice, right? So you had seen an R followed by an R, and that led to the grant. Is that what?
Yes.
Okay, sure.
So that is the deficiency of maybe, if you're hinting at that this grant is kind of covering only that request and maybe not that one, you can see there's a deficiency of LTL that it can't count. Of course, if you're interested, you can introduce a logic with counting, and some people do so. And in principle, you can think of a synthesis problem for that logic, where on top of the machinery that I'm going to show, you would have like a counter that you want to work with. And that is certainly a very fruitful direction that is not being paid that much attention to yet, because of course it's a bit harder. But I think actually these results that we're going to discuss today are pointing at some feasibility in this area, although not that much work has been done. Thanks for the question. This is indeed, you can see it as kind of overly simplistic logic, this LTL.
Okay, yeah, thanks.
Okay, thank you for the question. Okay, so next I'm going to very briefly put my glasses on, my glasses of someone who likes using machine learning, although not being a machine learning expert. And let me, to that end, tell you first what happens if, at least like 10 years ago, you take your favorite specification, you take your favorite synthesizing tool. Let me just call it synthesizer so that I'm not putting shame on any of the real tools. And what would happen typically would be that you would this tool would offer or would advertise a push button technology to solve the problem. And what would happen? You would push the button and you would get memoed, right? That's something that would be like a typical real life situation. If you were very lucky, or if you use a toy example, you would get a solution that is very complex, and you would even be in doubt to use it, or if you want to present it to your fellow engineer who wants to use it, then you would have a hard time convincing them to actually use it. So apparently there is something more that we need to do about this. And what I'm suggesting on a meta level is let's use a bit of learning in here. And learning is quite orthogonal, or the advantages and disadvantages are actually quite opposite to those of formal methods. So this is going to be a struggle, because these two worlds of formal methods and machine learning are very, very different, and putting them together is a lot of work. But I want to show that it's worth it. And I'm not going to bother you with too many details here. What I want to state here is that what we're hoping for from learning is the scalability that we are missing in the formal methods world. And we must at the same time be prepared to have way weaker guarantees from any machine learning subroutine that we're going to use than those that we are using in formal methods, where we are kind of used to the pattern where an algorithm solving a problem is simply solving the problem correctly and doing that at all times. Whereas learning is notoriously unreliable, and we have to take it as such. So the pattern that I'm going to introduce will be where these two communicate in a fashion where there is something that is a part of formal method that's providing some precise computation, some good data for this guy here, who is going to look at it and say like, I feel like maybe you should do this or you should do that. I'm not very sure, but I mean, just try it. And this is like a hint that we are badly missing in the formal methods community, because it's typically very hard to formalize what is even a hint of something that could work, but not necessarily. Okay, so now let me get a bit more into what has been done over the past many years in LTL synthesis. So already from the times of Church and Büchi and Landweber in the 60s, the approach was automata theoretic. That is very much in line in the development of computer science in those days, and also very natural in the light of properties as the one we discussed, where we intuitively need memory. And if we want to synthesize finite objects and work with finite objects, then the best representation that people have come up with is simply finite state machines, finite automata. And there is very close correspondence of logic and automata that most of you know, and that I will not dive into, except that I want to depict here the very concrete illustration of how an automaton is capturing this property. Essentially, if there is a request coming, then we need to change our state and to one where we remember that we are now supposed to emit at some point a ground. If we do so, we can come back to the state where we are happy even not ever issuing any ground. But as soon as there is another request coming, again, we have to come back and wait for the ground. If there are more requests coming, then you see, I mean, they're just accumulated here and they're flushed with a single ground as we discussed it. Okay, so this is capturing exactly the same, and there are automatic procedures doing that, and we will dive into that. Now, the next step conceptually is to turn this automaton into a game, because as you recall, while request is governed by you, I am the one deciding about the grounds. So if you are the environment, then here you are possibly emitting a request, and and then you can decide to do that, or you can decide not to emit a request. In either case, it's now my turn, and I can again respond either with not doing anything or issuing a ground. If you didn't emit a request, it actually corresponds to the loop here. And that's why also after you move me here, I go back here. So this, what we are doing here is we are splitting this transition that goes under the combined alphabet into the two parts. The one that input player is acting on and the one that output player is acting on. So this is always going to be in the shape of alternating between the input and output. So we're just splitting the edges by introducing the explicit output player's location. So the same is happening for all the other ones. And then now the green one here corresponds to the pair of green states here. So this is now a game. And if I can win the game, then there is a strategy of mine that gives the controller the circuit as Church required. We also cannot put it as a circuit, which means like a specific form of the output automaton, essentially. or you are winning, and then the answer is no, one cannot win, and then I mean your circuit, your strategy would be out. So that is a solution that has been on the table since early 60s. Now, or I mean mid 60s. Now the trouble is that the pipeline is quite costly. First, we have to go from formulae to automata, which, given that they're deterministic, or we require deterministic ones because otherwise it doesn't really play well with the game, is a double exponential construction. And second, we're getting something that is a parity game, and then we are actually solving it theoretically not so nicely. Practically, this is actually not much of a problem. So if you really construct the game already, then typically solving it is not much of a practical issue. Yet this is the bottleneck. The automata can be very large, even for very tiny formulae. That has triggered much of research in various areas, how to circumvent this issue. One obvious direction is like, let's consider simpler formulae than a whole of LTL. Maybe then this is not doubly exponential. So there have been works identifying single exponential fragments. There have been works identifying like GR1, identifying even polynomial time fragments that are practically relevant. People have been also looking at trying to circumvent, because this transformation is typically, as we shall see, done via Safra's determinization. People have been trying to avoid that determinization that is notoriously hard to implement by transforming it to various problems on Büchi automata. So there are approaches looking at emptiness of tree Büchi automata. There are approaches trying to look at larger and larger solutions to avoid the general kind of approaching it generally right from the start. Rather try to find a small solution. If there is one, then you can find it quickly. If not, then you try to find a larger one and you iterate like that. There have been approaches that are tightly connected to that transform actually this into a problem of emptiness of Kobuchi automata of various sizes. And actually these tools have been pretty successful, much more successful than this pipeline since the 60s. And this has been the case until I would say around 2017. Simply the traditional approach wasn't feasible. Let me tell you why, or wasn't really implemented as a feasible. Let me tell you a bit more about why. So I always am very happy to thank my friend and colleague from more than 10 years ago, which one day asked me, Jan, I'm working with this PRISM tool for probabilistic verification, and I'm checking these very simple fairness constraints, and it just works perfectly if I have one, but it doesn't do anything if I have a conjunction of 2 or 3. And can you tell me what is happening? And if you look at the probabilistic model checking pipeline, it proceeds similarly as the synthesis one. It also needs a deterministic automaton. So we were wondering what is going on. We looked at how the formula is translated to a non-deterministic automaton. The sizes were okay. I mean, this is just something that you can draw by hand. So what is the problem? But now we saw that the implementation of the determinization step by the back then state-of-the-art tool and the determinization of Safra with all its improvements back then actually didn't really terminate even for a few dozens of states in the non-deterministic. So the exponentiality was more than really present. It was really showing itself in its full glory and destruction. And this actually makes the whole pipeline completely failing in practice. So one point is it's very inefficient. And another point, as Orna Kupferman phrased it very neatly, it's so messy. I mean, the construction is basically destroying all the structure that you have in the automaton. It's very complicated. It's a tree over sets of states with labels and numbers and flags. I mean, it's complicated. So the point is, maybe there can be a direct translation. And in about 2012, we managed to get one, which actually put us back to numbers that are more realistic for any practical applications. And then there was plenty of research doing more and more. There is a whole zoo of automata that are out there that help you to get to deterministic parity automata, which are kind of the one used in synthesis. You can also use deterministic Rabin automata. These are kind of the ones used in probabilistic model checking until a few years ago. We have also worked quite a bit on limit deterministic Büchi automata, which have proved to be extremely useful for reinforcement learning of LTL these days, because there you can't use these guys that easily. They're too complicated, but non-deterministic Büchi automata don't work. So limit deterministic automata, limit deterministic Büchi automata are kind of the automaton model to be used in reinforcement learning. So all is now much brighter. We have very small, compared to previous situation, very small automata. On top of that, with logical structure, something that I like to call semantic labeling of the states of the automaton. And for that, let me give you a tiny example of that. So imagine that your input formula is something like this. Well, so let me read it for you. Either it holds that A does not hold at the moment, or infinitely often you want to see A followed by a B. What the Safra construction gives you is like some messy state space where you don't know what you're doing. In our direct constructions, you actually see that you have this goal, and then you have a sub-goal, which is something that is supposed to be repetitively satisfied. Now, if you see that A does not hold at the moment, so if you see an empty set, for instance, then you immediately go to a state where everything, where you're completely happy. You are left with true as the goal now, and you don't have to do anything. I mean, you just can do whatever. If A is happening, then in the next step, you're left with repeating A followed by B infinitely often over and over. But at the same time, you have seen an A. So now for this sub-goal, you are supposed to satisfy a B. If that is happening, then you have satisfied this sub-goal once, which doesn't mean much because you still have to do it infinitely many times, but at least there was one success. So in that case, you can go with a B and you're happy about your sub-goal. Your main goal remains the same. If you follow with an A and not B, so I mean, maybe you just go like this, then you stay here. If you follow with an empty set, then you're actually going to the same goal again, but now your sub-goal is to actually go with A and next B again, because you have failed that try, and then now you have a new one. So now you have to start from scratch. So this is roughly what the kind of information you have in the state.
Sorry, Jan.
Yes.
So is the empty transition allowed from that, because you have to see a B, right?
Well, it is telling me that if I want to satisfy the sub-goal, I want to see a B. If I fail to do so, my sub-goal is violated. But that does not mean that, sorry, I have to just plug in my computer. Just a sec.
So Deepak, I think you can have some instances where A is not followed by a B, right? That's allowed.
Okay, that semicolon is like what's not a conjunction of goals, is it?
No, I thought it was a sub goal.
So I deliberately refrain from giving like a semantics of this. The structure here is actually not so simple, but I mean, in principle, it consists of two parts. One of them is perfectly easy to understand, which is the formula to be satisfied now. If you satisfy that formula, then you should accept. If you don't satisfy, then the automaton says failure. The second part is more complicated. I illustrate this here only very, very briefly to give you a flavor of this. The idea here being that you have additional information on satisfying the subgoal. If you now don't see the B, it means in one of your infinitely many tries to satisfy this, you have failed. But I mean, you have infinitely many more to go. So if you have failed one, it doesn't really matter that much. You just start from scratch there with your sub-goal, and maybe next time you're luckier. Does that make sense?
Oh, but you've come to the state after having seen an A, right? So you better see a B.
You better see a B, exactly. Thank you for saying it exactly like that. You better see a B. If you see a B, you're happy because you have satisfied this once. I mean, there are still infinitely many to go.
Oh, okay, sorry.
But you have seen it once, and that's great. You like it. As a human, you like it. As a machine or as an algorithm of LTL synthesis, you may not jump out of joy because you don't even notice really, but you should like it. Whereas this one looks like, I don't want to do that. I'm wasting my time here. I better see a B. It's not failing because I mean, I'm just failing my sub-goal and I can try again. And now if I start doing A's and B's over and over, I can still win. But it wasn't a smart move. Does that make sense?
Right. So in some sense, there's a choice. I mean, there's a kind of a non-deterministic choice here. You can either...
Yes, you can see it. You can see it that way. Yes. I mean, think of it as now the whole alphabet is under the command of the output player, and the output player can choose the letter. I should have phrased it in this setting because I'm talking about the automaton, but I mean, you're maybe thinking in terms of the game. So in terms of the game, let's think about all these as all the letters, both A and B, as both atomic propositions as under the command of the output player. So you have a choice. You can choose A or you can choose B, or both or none.
So when you see a B and you go to that state, that will be like a final state. You can flash green.
Yes, if you see a B, then I mean you kind of see, okay, I've satisfied this one. So you are happy here, but then actually what happens is you should start all over. So now in the next step, you will again generate this sub-goal and you will try to satisfy it. And once you succeed, then you start satisfying it again and again and again, so that it goes infinitely often.
Right.
If you fail, you also start again, right? And with every success, you can think of it as you're in a Büchi accepting state.
Right.
Okay, does that make sense?
Sure, thanks.
Okay, cool. Thanks for the question. I think this is good that we clarify this. Here I want to give you a flavor. So I mean the labeling, depending on which of the many different translations these days you're using, it may look a bit differently, but I mean this is the flavor of it. Now, what does that mean in the whole pipeline? So, on the one hand, we have this transition being now not doubly exponential. Typically, I mean, in the worst case, still doubly exponential, but typically very reasonable. Yet it can still produce very large automata. Together with solving the game in not really, say, linear time, but I mean something that makes you work a bit, is still, well, pushing the boundaries much more to feasibility, but still it's not super great for practical purposes. And this is already enough to beat the previous approaches, but not really to be practical enough. Now, the idea here is, if this is still too large, what about not constructing it? What about constructing it on the fly only? And if you have a part of the game where you can already determine who the winner is, you don't need to construct the whole thing. Classical on the fly approach. So now this part where we are generating, the automaton, we are solving the game, outputting the result, that is now refined into this loop where we're exploring. You can explore the automaton and thus the game. You can solve the part of the game that you are seeing. If the winner is already determined, you know the answer, that's good. If not, you need to be exploring a bit more. Okay, so very classical on the fly approach. Now the question is how to implement this nicely. If you think in terms of exploring the graph or the automaton or the game, then it is a node that has outgoing edges to other nodes. Classical on the fly exploration would just go to the left or to the right or wherever. You can choose randomly. But which one to choose so that you're doing a reasonable choice, so that you're going in the right direction? Well, that's exactly where the semantic labeling, where this extra information can help. Exactly as Deepak said, you better do B in this situation. You exactly need this kind of advice. There, it was pretty clear that you want to finish the subgoal. There was nothing else to do. But now imagine this complicated formula, right? So either, so you can do A or not A for simplicity, right? Should you do A or not A? You see this very complicated formula. What should you do? Well, it's not really clear. You may see like, okay, what happens if I do an A? And what happens if I do a not A? In this case, you get a formula like this. In this case, you get a formula like that. Which one is better? Well, this is hard to tell. Depends on whether B is under the system command or the environment command, input or output player. It depends on how complex it is to satisfy these tasks. Yet a human would tend probably to go for FB, although there is no implication in between the two. It's not like one is simpler than other in general. You need a hint, and a human would say like, well, try FB if you don't know anything more. And that's exactly the task for machine learning, or for some heuristics that can help you. If they fail, they just advise you in the wrong way, like you try this one first, actually maybe this one was better, but then, you explore it next time, right? Nothing bad happens. So this is where you can safely use machine learning. Now, so that's the idea how we can employ machine learning. It will tell us where to go next, and actually we need to use formal methods to train the machine learning models that tell us which way to go. We need to, for instance, generate games based on formulae that are occurring in practice, and then you want to generate games, solve them, and maybe learn from the results so that you train the model. So this is the high-level goal. And then in the remaining time, I'm going to show you a few different ways how to explore in that direction. So for now, the main message so far is there is more information in the automata than there was before, which allows us to use learning. And this information, by the way, has been there in the non-deterministic Büchi automata, but it is obscured by the determinization process. So you may be doing something like that in model checking, in standard model checking of non-deterministic systems. But in probabilistic model checking and synthesis, this was not possible because it wasn't there in the deterministic version. Now we have that extra information, and now we can plug in machine learning there. Now, how do you figure out, I mean, again, if you have these two options, how do you figure out which one you want to go for? And then you can have plenty of ideas, right? One of them would be, okay, let's very simply see the formula, be it a temporal formula. Let's see it as a Boolean combination of two things, like one and an A here and GFA here. Let's forget about the temporal structure of this. I mean, this is just one thing and another thing. Let's see just propositionally. How hard is it to make this work? Well, you have to make this work, the first thing, and you have to make the second thing work. So it's like, I mean, if you have a random assignment of to this proposition formula, it's like 1 in 4, which is worse than if there was a disjunction. That would be 3 in 4, right? So that's a very naive thing, but actually already that, although it ignores whom belongs the atomic proposition, is it the system or is it the environment? It ignores the temporal structure. It ignores many things. This already actually beats, this guidance already beats all the previous approaches. And this is also what is in the heart of the tool Strix that has been winning the LTL track in the recent years. And it is interesting to see that with that, for many cases, you already can guess a winning strategy without even looking at the graph. So you only are going to go for better trueness, and you're only going to choose the successor that has the best trueness. So you're going to look at all the successors, you look at this very naive heuristic of trueness, as we call it, and you're going to choose the best one, and this is going to be your strategy. I haven't even seen the automaton. I just tell you, this is my strategy, and actually in quite a number of cases, in benchmarks, it's already generating a winning strategy, whereas a random assignment is not, I mean, that effective, obviously. But of course, you want to do more. You want to employ machine learning that looks at more features and looks at, as we've discussed it, some other games that have been generated and solved, and it tries to mine from those games what are the winning and losing decisions. Which decision is better in each state? And it tries to generalize it so that next time it sees a labeling of a state, it knows where to go. For that, I mean, you can definitely use different models, and we have tried a number of those. It is interesting to see also open theoretical points here, as if you want to say which edge is better, it's not always trivial, right? You don't have maximum permissive strategies in LTL games. So from the theoretician's perspective, this is quite interesting because you can have one winning strategy that goes like this. Oops, sorry. And here. So in this state, I choose like this, and here I go back, and in here I go there, which is perfectly fine. You can also have one that is going in the opposite, I mean, in a mirrored way. So that is going like this, this, and that. Sorry, I should have used a different color. Let me just use a different color. This, and that. But obviously, you can't say that these backward edges are fine, so that these backward edges are fine, because if you use them both, then you will never get to the target. So you will always come back, and then you can end up in this infinite loop without reaching the target, really. So is this a winning edge or not? I mean, you can use it in some winning strategies and not in some others. Then how do you approach that, right? When we don't really have maximum permissive strategies for LTL objectives, we only have that for safety objectives. So this is like what theoreticians need to figure out. I mean, how to work with that. We have used support vector machines with more features. I mean, you see the percentage of giving you the right answer right away is then much higher than the naive heuristic. I'm not going to go into the details here. we have improved that even more and applied it to the data from SynthCom. So this is the synthesis competition, standardized one. And it turns out that even there, for quite a realistic formulae, we can often solve the game without really even looking at it. So we can guess the winning strategy by saying, we use this machine learning oracle that tells us which way to go, and we don't even want to know what happens next. We don't even construct any automaton. We just follow this advice. And in a number of benchmarks, 85% of the benchmarks, this is a correct solution, which is quite amazing, given that these are reasonably realistic formulae. Of course, the key is to attack the remaining 15% of the complex formula. Now, so again, let me summarize up to this point, and then let me conclude with the current work. We have seen that the translations can be now made way cheaper practically. The information that is now preserved allows us for heuristics or oracles that give us a kind of initial guess where to go, and allow us to plug that into the framework of synthesis. Now, what is there are more things to now think about. For now, we have discussed what is our first guess. Now, if that guess doesn't work out, how do you proceed? Well, there are a number of ways how to go on from here. One of the approaches is, you can apply Q-learning, which is a partial, on-the-fly exploration technique. And let me just say here that Q-learning actually sucks if you use the vanilla Q-learning. It's here is the number of benchmarks that you can solve, essentially. So the higher, the better. Compared to things like strategy iteration, the golden standard of verification people. But if you actually apply Q-learning with this extra information, it's now way better. Even if you actually only look at very, very simplistic semantic information, like maybe the trueness. So this can help. Another way how to proceed from here is, and that is, I'm happy to announce our new tool that has won this year's SynthComp, that actually uses support vector machines and, more importantly, gradient boosted decision trees to actually learn from previously solved games. And then, despite Strix being then up to then the winner for a number of years, because also being very, very well engineered. So because of its engineering, is like 5 times faster than a prototype that we would that we currently have. Actually, by some algorithmic improvements and this learning, we can now solve more benchmarks, although now still by not very large margin. More importantly, we are way faster on complex benchmarks. So we are 10 times faster on synthetic data. On the real data, still something like 3 times faster on the complex benchmarks, while being way slower for the easy ones, because there is the overhead of our approach and the kind of starting of the JVM and all the starting of the learning models and all that all the overhead that we are getting while using machine learning. And for the main important message is that for the more complex ones, the machine learning then pays off, which is also behind then this year's winning. So let me conclude then. The key information is we now have more information in the parity games. Then we shouldn't just use parity game solvers as they were, but we should help them with learning heuristics. We are doing pretty well already on the level of beating others, but actually, I must say, we are still just scratching the surface. Learning formulae is hard. I mean, they have very discrete structure of, I mean, you can think of the syntax trees. I mean, something that is very hard to learn. So there is much more to do in the realm of learning, and there is much more to do in the realm of theory. For instance, even figuring out which edges are so-called winning and which are losing is, in the presence of non-permissive strategies, something that theorists have something to say to. So there are plenty of directions, and with that, I am happy to answer any questions that you may have, and I want to thank you very much for your attention.
Yeah, thanks, Jan. Thanks for a wonderful talk. We do have time for questions. If there was one question in the chat, but I think you had answered that while answering Deepak's question.
I have noticed. Okay. Yeah, I mean it was indeed. I mean, the structure can be quite complex. In that case, I was deliberately choosing something that you can indeed interpret as I want to also do that. But I mean, if you fail the other one, it's it's not a disaster. So it's like a soft constraint then. So it's not really an end.
Also, this other comment that you had about maximally permissive strategies. So you're saying
Yes.
that given two strategies, you cannot compare which one is more permissive.
Exactly. So I mean, here, I mean, you have the black and the red strategies. Of course, none of them is kind of the natural one. I mean, people would. I mean, if you're starting here, the natural one would be this one. But of course, it's very hard to say what that is. Of course. Sorry.
Yeah. So no. Sorry.
Yeah. Of course, you can think in terms of like when computing attractors, you want to like take the shortest path and so on. But it's really, I mean, it's a really intriguing question. Should I say that this edge is bad, or should I say that this edge is bad? Is any of them really bad or not? I hesitate to say that it's bad because it's still useful in some strategies. It's not maybe the best or most natural choice, but how do you even define like the status of such an edge? I mean, is it learning people just put some number on it, right, and then see what comes out? But I mean, as a theoretician, I'm not happy with this approach, right? I don't just want to throw around numbers and showing like, oh, in the resulting benchmark, it works 10% better than the previous approach. And no, I want to have like a clear status of what is a winning edge, what is a losing edge, what is something in between, what is the theoretical implication of having incomparable strategies, and how to work with that. And I think we are missing like theoretical underpinning of all that. And with more theory, maybe we could actually design more systematically the learning approaches.
Okay. So are there other ways to compare two strategies, or is that also?
So what we are actually doing now is we are thinking in terms of, well, the shorter the better. So what we are practically doing is we are looking at the different strategies. We're generating different strategies so that we're not kind of missing out on these edges or missing out on the shorter winnings. And whenever there is a shorter path to the winning states, or I mean, to kind of some partial, I mean, in here it's reachability, so you know where you win. I mean, if it's repeated reachability, you just have to go with like accepting state or something. So these partial kind of evidences of going towards winning. And we are employing something that is called beta decay, which is essentially discounting of longer paths. So a longer path is not so helpful as a shorter path, which is not always necessarily the case, but it's practically kind of useful. But again, I am missing some more theoretical approach, more systematic approach to this. This is just like first thing that comes to mind. Longer one is not so good, so maybe let's make them more, I mean, deterring. But again, this is not enough.
Yeah, sure. Thanks. I think we do have time for maybe one or two other questions.
Yeah, I have a question. Am I audible?
Yes.
Yeah, please go ahead. Yeah, I can hear you.
Yeah. Can you tell me exactly what are the features that you're talking about and how you're generating the data set on which you're training the machine learning model?
Okay, so the features that we are generating are partially hand produced. So I mean, the ideas based on which we generate the features are, you can think of like how deep is the Boolean, the tree of the Boolean representation of the formula. How many formulae, how many atomic propositions are owned by the system versus how many are owned by the controller. How many disjunctions as opposed to conjunctions are there? I mean, there are plenty of things that are just like a completely randomly generated manual things. We are then producing automatically somehow their combinations and their twists. And then once we generate plenty of those, I mean, it's thousands and thousands of features, we are actually extracting a few, like in some experiments, dozens, in some experiments, just like 10 of features that are the most important ones, which we are then using for learning. Because then the excessive number of features is not, I mean, necessarily helpful. So then these are also not generated in a very systematic way, right? I mean, people don't know. I mean, there are works that do learn formulae, and we have also been working on that, but no one really knows how to learn formulae well yet. So these are completely wild features, and then we build on top of that SVMs or neural networks and various models. And so this is, again, very much open to more systematic approaches. Have I answered the question, or were you asking them more in the direction of the models?
No, it's fine. Yeah, I got it. Thanks.
So, Jan, sorry, I missed part of the talk because I got thrown out from my internet. But how exactly do you repair a wrong? Your model, the machine learning gives you some controller. How do you, which is not satisfying the property?
So the point here is that if you mess up, what does that mean? Then it means that you have explored something that was not as useful. So maybe this choice then leads in the game to defeat. So then actually what you wanted to do is to explore also this one so that your strategy chooses the other one. So in that sense, you are not really doing anything wrong. You're just exploring in the non-efficient order. So your on-the-fly exploration is leading to a part where you can't profit from that. So you need to be backtracking there and exploring a different part of the game where you can enforce winning. So in that sense, it just slows down the process, but it's not jeopardizing the correctness of it in any way. Does that answer it?
So backtracking means you have some kind of tree of possible choices in mind, is it?
Right. Okay. So how do we do that? Well, you basically have to say where do we, if we fail, where do we explore next? Say we explore this one, but I mean then we explored another one here, and I mean maybe some exploration was happening from some other state. So where do we explore further edges? In here, or maybe in here, or in here? And then what we do is, again, we ask the machine learning oracle which of these states actually is somehow good, and we have a good chance of winning there. And while from the next state we have messed up. So I mean, it looks like, I mean, the chances are lower here than there. So then we can actually kind of say, okay, maybe that wasn't a good choice. Maybe if this one is almost of the same quality as that one, maybe let's try to explore that one. But again, I believe that more theoretical work on game repair, if you will, like a repair in the sense, like, I mean, you have a strategy that is failing, then how to pinpoint places where you're going wrong. More theory on that is required so that we can again have a more systematic learning procedure for figuring out where to backtrack. So we're using currently a heuristic, and we would like to be more systematic. That's the summary of the answer.
And these are all memoryless strategies on the.
Beg your pardon?
These are memoryless, only looking for memoryless strategies.
Yes, we are looking for memoryless strategies because the automaton is making sure that we have a memoryless strategy on that graph, on that game.
Mm-hmm.
So yeah, but certainly, I mean, there was this question at the beginning: what about the counter, right? And you would be thinking in terms of a strategy with a counter. Sure, that would also be quite interesting.
Yeah.
Okay, so if there are no further questions, let's thank Jan for a wonderful talk. Thank you so much, Jan.
Thank you very much again for the invitation. And if any of you is excited by these questions, be the machine learning part or the theoretical part, get in touch, and we can discuss more. I will be happy to talk more. And with that, thank you very much. I will have to run now. So thanks, and yeah, have a great time. See you soon.
Thanks, Jan. Yeah, thanks for the talk.
Thank you. Bye-bye.
Bye.